Hello, my name is Bill Kinney. I'm a math professor at Bethel University in St. Paul, and this is part 13 in my video series about multivariable calculus using the computer program Mathematica. It's also part 13 of a sub-series about calculations with parametric curves. The focus of this video is to parameterize what's called a piecewise-smooth curve using piecewise-defined functions. I'm going to make use of some of the code that I showed you in Mathematica from the previous video, number 12, to visualize this better, so you might want to watch number 12 before watching this one. Here we are. Here's our example, example 13. Find a piecewise defined function, c of t equals f of t comma g of t, so we need to find f and g, that parameterizes a triangle. You're probably going to want to get a piece of paper out and draw this triangle on your piece of paper. We're starting at the point 1, 0, when time is 0. We travel to the point 2, 3 as time increases from 0 to 1. We go to the point -1, 5 as t increases to 2, and then we end back where we started when t equals 3. So draw the triangle, and we're going to need to think carefully about each individual coordinate, x and y, as we move along this triangle to come up with these piecewise defined functions f and g that is going to model this motion. To get a piecewise defined function in Mathematica, there are a couple different ways you can do it. One way is with something called the which command, W-H-I-C-H. But I prefer using this basic Math Assistant palette. Over here, there's a button right here that I can click on, and it comes up here as a piecewise defined function kind of symbol. We can add a row to this, which I'm going to need to do because I've got 3 pieces for a triangle. You can do a control return to add a row to this. In the second column, what you want to put is you want to put the conditions on time, in this case, for each piece of the function. The first condition is t goes from 0 to 1, so I'll type a 0 less than or equal to t less than or equal to 1. Then I'll tab over to the next row in the second column. The second condition is t goes from 1 to 2. Let's not include 1 in that since I already included it in the previous case, but we will include 2. The last case, t goes from 2 to 3. I can type it like this. I now want to find expressions, formulas for f as a function of t for each of these 3 cases. So think about it. Focus on these first coordinates. The first coordinate changes from 1 to 2 over the first interval, then from 2 down to -1 over the second interval, and then from -1 back up to 1. In other words, over the first interval, it increases by 1. It's got a rate of change of 1, and it starts at a value of 1 as well. Think about that. T plus 1 will be a quantity whose rate of change with respect to t is 1 and starts at 1 when t is 0. You can see it has a value of 2 when t is 1. This is going to parameterize the first coordinate over the first time interval. Now think about the second time interval. X is going from 2 down to -1 there, as t increases by 1 unit from 1 to 2. X is going down by 3. The slope, the rate of change with respect to t, is -3 in this case. It's starting at a value of 2 when t is 1. One way you can take care of that, I encourage you to try to think about this on your own, but if you type a t minus 1 here in parentheses and then do a plus 2, that'll be an expression that has a rate of change of -3 of x with respect to t. It's going to have a value of 2 when t is 1, and you can check that it will have a value equal to, let's see, -1 when t is 2. Will be right there. Finally, over the last interval, t goes from -1 back up to 1. It increases by 2 over 1 time unit. Its rate of change with respect to t is 2. It's starting at a value of -1 when t is 2, so I can type a t minus 2 in parentheses here, -1. You should double check that that is going to work. That'll be a formula for f. G is going to be something similar. I will copy and paste the formula for f over here for g, but now I'm going to need to change these formulas. The intervals will be right though. Now focus on the second coordinate. Y starts at 0 and goes up to 3 over the first interval of time, so its rate of change with respect to t is 3. 3t will do it. That'll start at 0 and go up to 3. Over the second time interval, y goes up by 2 as well, from 3, actually goes up by 2 this time instead of 3. From 3 up to 5. Its rate of change with respect to t is now 2. It's starting at t equals 1, so I put a t minus 1 here, and I put a plus 2, focus on the y, excuse me, plus 3 after that point that is an expression that will have a value equal to 3 when t is 1 and go up to 5 when t is 2. Think about that. Pause the video if you need to. Over the last time interval, y goes from 5 down to 0. It decreases by 5. The rate of change with respect to time is -5. Starting at t equals 2, and the initial value at t equals 2 is 5, so I now put a plus 5 here as well. That is now a quantity that will start at a value of 5 when t is 2 and go down to a value of 0 when t is 3. You should think about that. Alright, that does it. We can now enter these functions, f, g, and c as a point, a list in Mathematica. I can enter all this code that I showed you from the last video to create the different plots that we want here. Ultimately, our animation for this situation, which I now didn't need to make smaller, looks like this. We're going to have our triangle in the upper left corner. Y is a function of time in the upper right. X is a function of time in the lower left, though we don't see the complete graph. I couldn't quite get it to make the complete graph. I'm not quite sure why not. And then the distance and speed as functions of time in the lower right. Actually, I know a trick. Maybe I can try this trick to try to make the entire graph. If I make the speed and distance graph with an image size of large, that might do it for us, because that'll make everything on the bottom larger. Nope, didn't quite do it. Oh well. Let's go back to changing that to medium. Sometimes you are not sure what's going to work, so you just got to try different things. It is kind of herky-jerky there in its motion. You can get it to be smoother. I'd like to spend a little time showing you how to make it smoother. And basically it's the n integrate that's really slowing it down. So it's doing lots of calculations and calculating this distance function, but I'd still like to see the distance function here. The distance function comes from integrating the speed. The speed is going to come from taking the square root of the sum of the squares of the derivatives of f and g. We can create a formula for the distance traveled as a piecewise defined function here as well, and I can use the same kind of, actually let me just copy and paste these here so that we get the intervals right away. We got to just change these expressions to the correct things. And you can just think about it piece by piece. In fact, think about what the speed will be over each piece. Over the first interval of time, the speed in the x direction is 1 and the speed in the y direction is 3. Actually, I should think of those as being velocities because we're going to have negative velocities in here as well. Based on the fact that how I taught you about calculating the speed of the square root in the past, you should do something similar over each piece. The derivative here is 1, the derivative here is 3. For the first interval of time, 1 squared plus 3 squared is 10. Square root of 10 is going to be the speed over the first time interval. If I multiply that by t, I'm going to get the distance traveled over the first time interval. Over the second interval of time, the x velocity is -3 and the y velocity is 2. If I take -3 and square it to get 9 and then add 2 squared, you're going to get 13. Square root of 13 is going to be the speed over the second time interval, and if I multiply this by a t minus 1 and then with a plus square root of 10 in here, this will give me my distance traveled for times between 1 and 2. I'd encourage you to think about why that works. In particular, why did I put a square root of 10 there? Finally, over the last time interval, the speed will be the square root of 2 squared plus -5 squared, which will be the square root of 29. I can multiply that by a t minus 2 and then add square root of 10 plus square root of 13. That quantity is representing the distance traveled up through time equals 2. That'll be my distance traveled function. Now this animation is going to run more smoothly. We will see, even with my slow computer, yeah, that's a smoother animation. And you can see the distance traveled in the speed graphs over here as well. The speed graph is piecewise constant. ignore these vertical pieces. It actually is undefined because the derivative is undefined at 1 and 2. The blue graph, the distance traveled, looks straight. It's not. It's piecewise linear. You can see in the last piece it's a little bit more clear that it goes up at a higher slope. Here's your exercise. You should now try to find on your own a piecewise function. Also parameterizing a triangle, starting at a certain point, going to another point, and then another, and then back to where you started as time increases from 0 to 1, then 1 to 2, then 2 to 3. And I've got an explanation here. Here's the formulas for f and g, and the formula for the distance traveled function. I can enter those things now as well, and enter this stuff. It might be the same as the last one, so I might not have had to have entered that. And here's the picture for your problem. This is what the parameterization should look like. And again, I apologize that the lower left graph, the sideways graph there, isn't a complete graph, but it was good, as good as I could figure out for the time being.